So good morning all. So today we are going to discuss about a MIPS instruction set. So MIPS stands for million instructions per second. So usually MIPS is nothing but it is used to store the instructions during the conversion of a high level language into low level language. So what is the main use of this MIPS? So the main use of MIPS nothing but so when we are going to program for any task, right? So for example, consider Fahrenheit to Celsius. So the data is what we are going to use, data types what we are going to use, input output what we are going to use. So all the things is going to be converted into low level language. So during the conversion, so this instruction set helps in storing the data, storing the instructions, storing all the input output statements, storing the functions, data structures. Everything is going to be stored in this instruction structure. So this is the normal architecture of a machine structure. So here if you take, you have two levels. One level is software, next level is a hardware. So software is nothing but it is a application side. So application side is where we are going to use, the user will be using any high level language like C, C++, Java to perform some task. So in this case, for example, consider we are going to use a C or C++ to convert a Fahrenheit into Celsius. So there what happens, the program will be written in the software side, the application side. So after writing program, usually we'll be compiling it, right? So what will be compiler? Compiler is nothing but it is the one which is going to convert your low level language into, sorry, high level language into low level language. So during the conversion, it is going to mainly check the syntax and semantics of the particular programming language. So then assembler is nothing but the OBG, right? So it is going to be converted into the assembly level language. So then you are going to have a OS. OS is the one where all this compiler, assembler, everything is going to be operated. So this is a software side. So next to hardware. So if we take a hardware side, what we are going to have, so all the processors, so the memory, input output systems, data path, designs, transistors, resistors, registers, all this comes in the hardware side. So here what is the use of this instruction set architecture? This instruction set architecture is going to act as a bridge between the software and the hardware. So when any high level language is written to perform any task, when it is going to be compiled or executed, it is going to be converted into low level language, that is the machine level language, because machine does not understand any high level languages like C, C++ or any English statement like printf, scanf, cout, cin. So machine understands only zeros and ones. So whenever any high level language is written to perform any task, it should be converted into the low level language. So while it is conversion, so the instruction set is the one which is going to hold all the data types, data structures, what is used in the program, right? So that is the main use of a MIPS instruction set. So this is the instruction set architecture. So usually instruction set architecture is nothing but it is a family of the microprocessor. So examples, if we take Intel, SunSpark, DEC Alpha, IBM 360, these are the various examples of a instruction set architecture. So ISA, what are things it includes? It is going to include the instruction set. Next, it's going to have a rule for using instructions. Then it's going to specify the mnemonics, functionality, addressing modes, and encoding. How it is going to be encoded. So this is the main use of a ISA. So MIPS, if you take, mainly it is going to fall it in a five classes. So one is it is going to be in a arithmetic, logical, shift, comparison, control structure, control instructions, limit, branch and jump, load and store, and exception, register movement, everything. So here usually if you take three types of encoding formats we are going to have in a MIPS. One is a R type, I type, J type. So each and every type is going to be 32-bit long. So if you take a size of a instruction set, it is going to be a 32 bits, right? So this is the normal things you're going to have. So if you take a R type, you're going to have a six components, right? So first one is nothing but a function, that is starting from 0 to 5 is going to be a function. So what function you are going to perform, whether we are going to perform arithmetic or logical or shift, what we are going to perform, that is called as a function. It is a 6-bit function code. So next we are going to have is a 5-bit shift amount. So SHAMT is nothing but it's a shift amount. What type of shift operation we are going to use? Right shift, left shift, everything. So here if we take 15 to 11, so RD, RT, RS, Nothing but it is used to, this is three types of register which is used to store the input and the output. So here in this case, if we take 15 to 11, RD is used to store the first input, RT 16 to 20 is going to store the second input, RS it is going to store the result. For example, if we take, you are going to add two numbers A equal to B plus C. So B will be stored in RD, C will be stored in RT, and A will be stored in a RS. So the opcode, 6-bit opcode, it represents what type of operation you're going to perform. Whether it is going to be a arithmetic, that is arithmetic means addition, subtraction, multiplication, division, whether it's going to be a logic, and or whether it's going to be a shift operation, left shift, right shift, all this going to be indicated by this particular opcode, right? So this is the normal operations we are going to have. That is a format, opcode format, opcode RS, RT, RD, shift amount, function, and the address. So for addition, subtraction, add immediate, load word, store word. So load word is something where what happened is the word is going to be loaded into the particular compiler or assembler. Store word is we are going to store the word. So it is the format you are going to have. So all the add, subtract, add immediate, add and subtract comes under R format. Add immediate, load store comes under the I form. We will discuss this in the forthcoming slides. So opcode, if we take for addition, the opcode is 0. RS, RT, RD, I said about the three registers where RD is the first variable, RT is the second variable, RS something but a to store a result. Shift amount used is 0. The function is a 32. So if it is going, if we're going to put 32 means it indicates it is a addition. So if it is going to put a 34 means it's going to indicate it's going to be a subtraction. Okay, opcode is going to be a 0. Same like that, if we're going to put the opcode 8 means it indicates add immediate. So if it is going to be 35, opcode position, you're going to put 35 means it indicates a load word. If it is going to be 43 means it's going to indicate the store word. Okay, so this is a general example. Okay, how a MIPS, that is a machine level, any high level language, how it is going to be translated into the MIPS assembly level language, right? So we are going to see about for R type. So this is a normal version of a MIPS instruction set. Okay, symbolically it is going to be represented as add dollar T naught comma dollar S naught S1 comma dollar S2. So where S2 S1 are the two registers, input registers. T naught is nothing but it is used to store a result. Okay, so here this is the how the decimal representation is going to take place. For R type, if we take, we are going to have all the six fields. That is the opcode, RS, RT, RD, shift amount, function. So all these things, 6 bits will be stored. Okay. So first we are going to have a add T naught comma S1 comma S2. So for add the opcode, what we are going to see? So for add is nothing but opcode is 0. So here if you take, if you see this table for add, opcode is 0. For RS, RT and RD, you are going to use a register numbers, right? So for RD you are going to use a 8. For RT you are going to use a 18. For RS, that is the T naught, you are going to use a 17. So shift amount is 0. So function is 32. This 32 we are getting from here, this column. Okay, so this is how the instruction is going to be filled. That is, the six fields is going to be filled in a likewise in a R type. Then what happens? This decimal number is going to be converted into a binary. That is a zeros and ones. So this is how any high level language is going to be converted into a machine level language, right? So this is what I said. The first and last fields contains a 0 and 32, which tells the instruction perform the addition. Second field gives the register, that is the $S1 is something but 17, $S2 is something but 18, T naught is a 8. So normally you're going to perform it, right? So this is about a R type instructions. In R type instructions, normally you are going to have all the six fields, that is the opcode, RS, that is R the destination register, RT and RD source registers, shift amount and function. Okay, so this is about the R type. So next we are going to discuss about the I type. So what is the I type instruction? So here I type instruction, you are going to mainly have a four fields. So one is the opcode, next one is the RS, that is the first device, RT storage, then you're going to have constant or address. Okay, opcode 6 bits, RS and RT something but it is a 5 bits, constant or address going to be a 16 bits. Okay, so this is about the normal I type. So example, if we take, this is the example, dollar T naught comma 32 comma dollar S3. Okay, this is the example load word for I type. So how it is going to be placed in this in this field? So for load word, opcode is 35. How we are getting this 35? So we are getting this 35 from this particular table. See here. So if it is going to be load word means for opcode column, you're going to put a 35. Okay. So where RS is, it is a result, for storing the result. RT and RD is a source registers. Okay. So here what you're going to have, so one source register, one destination register. Okay. That is 55 bits plus 16 bits. Remaining 16 bits for address. So for load word $T0, comma 32, comma $S3, here what happens? So the first 35 is placed in the opcode for the load word instruction. RS, that is a 19. Okay, then RT, it is going to be 8. So why it is coming to 19? Because for T0 that value is 19. So for T0 value is 8 RT. RS $3's value is 19. So constant is nothing but a 32 bits. Okay, so how we are getting this 32 here? So because here load word example we are given 32, so we are going to put it 32 here. So this is about the I type. So in R type we are going to have all the 6 fields, that is the opcode, destination register, two source registers, shift amount and function, total 32 bits. So this is the fields you're going to have in a R type. So if you take a I type, you're going to have only 4 bits, that is opcode, destination, source, remaining 16 bits for constant or address. Same like for J type. So J type, if you take, you're going to have only 2 fields. One is the opcode, next one is the address. Okay, so opcode 6 bits, address is 26 bits. Okay, J type is something where usually it is a jump. So it is used for jump the instructions. Okay, so how it is indicated in MIPS? So J 1000, 10,000 means it is going to go to this particular location. That is the address. So opcode you are going to use is a 2. So this is the 3 types of R type, I type, and J type, right? So this is how the MIPS assembly language is going to be work. So the first slide, second slide, so we discussed about 5 types of MIPS instruction we have, right? So first one is something but the arithmetic. So arithmetic, if we take, mainly we're going to have 3 instructions. One is add, subtract, add immediate. So example, how we are going to write in MIPS assembly language for add? So add $S1, comma $S2, comma $S3. So what it indicates? So you're going to add $2 and $3 and you're going to store it in a $S1. So to perform this add operation, you are going to use a 3 register operands. Same like that subtract. So for subtract, what is the mnemonics you are going to use? SUB, sub $S1, comma S2, comma S3. So here what happens? $S2 is subtracted from $S3, result is stored in a S1. Same like 3 register operand. Same like that for things. So add immediate, what you're going to do? You're going to add a constant. Okay, so what is the difference between add and add immediate? So in add you're going to use the all the registers, whereas add immediate you'll be using a one constant value. So here what happens? $S2 is added with the 20, that is a constant value, then it is going to be stored in a $S1. So this is about your arithmetic. Same like a data transfer. So what is a data transfer? Mainly data transfer, if you take, these are the instructions you're going to have. So load word, store word, so load of unsigned, store of, load byte. So these are the various things. So normally you'll be using only these 2 things, load word and store word. So load word is nothing but what is the general format? So $S1, comma 20, comma $S2. So what it means? So in memory, the 20th location, memory location, this $2 is going to be stored, and it is going to be stored in S1. So in memory, this $S2 register is stored in a memory location 20. So how we are going to have S2 plus 20 memory location is stored in S1. Okay, word from memory to register. So store word, what happens? The same mnemonics only, $S1, comma 20, comma S2. So here what happens? Word from register to memory. Okay, so here word is going to be stored to memory. Okay, so this is a data transfer. So logical is something where you are going to have a and, or, nor, and immediate, or immediate, shift left logical, shift right logical. So these are the various logical operations you're going to have. So what is that? And $S1, comma $S2, comma $S3. So what it means? So you're going to and operate, that is the ampersand symbol, S2, comma S3, store it in S1. So you're going to use the 3 register operands and you're going to perform a bit by bit AND. This is same for all the OR, NOR, add, immediate, everything. Okay. Some conditional branch. This is very important. So conditional branch is nothing but you're going to use here four types of things. So mainly, one is a branch on equal. So branch on equal means what? You're going to use a if condition. Okay, if that is a BEQ, that is a mnemonics BEQ $S1 comma $S2 comma 25. What it means? Yes, for condition statement, it is a if. So if $S1 equals double equals S2, then you're going to go to the particular position. Okay, so PC is nothing but program counter is the one which is going to move the instruction to the particular location. The PC plus 4 plus, usually 4 is a constant value. So plus 100 means, so this is the location where the position of the memory. Okay, so PC plus 4 plus 100, then 25 is going to be added. Okay, same like that for branch on not equal. So branch on not equal, the keyword you're going to use is a BNE. So what is BNE? So branch not equal. Same mnemonics $S1 comma $S2 comma 25. What it means? If $S1 not equal to $S2, then go to the particular position. Okay, same way the PC plus 4 is a constant plus 100. 100 is something that represent at present where the memory it is pointed is, right? So that is the branch not equal. Same way the set on less than. Okay, then set on less than unsigned, immediate signed. Then finally you're going to have a unconditional jump. So you're going to have a jump. Okay, jump register, jump and link. So jump to 2500 means it is going to go to the particular location, like a target address. Okay, so this is how the instructions you're going to have in a MIPS. So now we are going to see how we are going to compile a C assignment using a registers. So usually when you are going to perform any high level language, for example take C language, usually what happens, I said in MIPS it is going to be converted into assembly level language. So to convert into assembly level language, MIPS mainly it is going to use a registers to store all the data, operands, everything. For example, if you take this instructions, so what is this instruction? You're going to have f is equal to g plus h minus I plus j. Okay, so here what are the variables you're going to have? The variables, if you take f, g, h, I, and j. So what are the operands you're going to operators you're going to have? So equal to, plus, minus. Okay, so normally what happens? All these variables going to be stored in a register. That is a dollar S0, S1, S2, S3, and S4. So they are asking what is the compiled code of a MIPS. So what will be the compiled code? So first what you're going to do? So you're going to perform a first operation, that is you're going to add a G plus H. So G plus H you're going to add and you're going to store in a T0 register. Okay, so first G and H it will be stored in a S0 and S4. It is what indicated here. Okay, so G, H, I, and J stored on S0, S2, S1, S2, and S3 and S4. Okay, so here what are you going to do? G and H will be stored in S1 and S2. This is the code. Add $T0 is used to store the result, comma $S1 comma S2. So now register T0 contains the value of a G plus H because G is stored in a S0, H is stored in a S1. Same like that. Next one, what you're going to do? I plus J. So I is stored in a $S2, J is stored in $S3. See here, $T1. So in T0 you're going to have a G plus H. So you're going to use the other next variable, that is $T0 register. Okay, $T0 comma $S3 comma $S4. Because in S3 you're going to have a I, in S4 you're going to have a $S4, you're going to have a J. So what you're going to have? $T1 contains the I plus J. So finally, what you're going to do? So you're going to subtract these two things and you're going to store it in a F. So F is going to be stored in a $S0. So what are you going to do? So you're going to subtract and you're going to store the result in F. So F is stored in a register $S0. So what you're going to do? Subtract $S0 comma $T0. Usually in T0 you're going to have a G plus H. In T1 you're going to have a I plus J. So what you're going to do? Subtract $S0 comma $T0 comma T1 means the F now gets the $T0 T1, that is which is G plus H minus I plus J. So this is how the instructions what you're going to write in a high level language is going to be converted into a MIPS assembly level language. So from here what happens is going to be converted into low level language, that is zeros and ones. So we are going to have numbers for everything. For add it is going to be 32, subtract is going to be 17, likewise. then it is going to convert it into binary. So this is how any high level language is going to be converted into the MIPS. Mainly in MIPS, we are going to use a registers to perform the operations, right? So this is the general examples how we are going to convert. So for example, you're going to have A equal to B plus C and D equal to A minus C. So this is how we're going to write a assembly level instruction for the following C statement, that is add B comma C. So B comma C going to add, the B plus C you're going to add, is going to store it in A. Same likewise, you're going to subtract A minus C. So subtract D comma A comma C. Okay, so this is the general examples. Okay. So the next, the important concept of MIPS is nothing but it is the addressing modes. So what is the addressing mode? So addressing modes is the one which is used to identify the location of the operand. So in the before cases we discussed about the operands, right? So where you're going to store each and everything in a registers, right? You're going to have two sets of register. One is a T naught register, one is a S naught register. Where T naught register is used to store the result, S not registers used to store the variables, right? So here addressing modes, if we take, mainly you're going to identify the location of an operand and which location that operand is stored in a memory. So usually to perform that, we are going to mainly have a five types of a MIPS addressing mode. So what are the five types? One is a immediate addressing mode, register addressing mode, base or displacement addressing mode, and PC relative addressing mode, pseudo direct addressing mode. So what is the immediate addressing mode? So immediate addressing mode is nothing but it is an operand or a constant within the instructions. So in instructions, you're going to have any constant or anything that is called as the immediate addressing mode. So in the instructions, you're going to have a register as an operand. You're going to have, we name it as a register addressing mode. Okay. So now we'll discuss each and everything. So immediate addressing mode. So immediate addressing mode, what you're going to see here, the operand is nothing but a constant value. You're going to have some constant value in a instructions. So then it is called as a immediate addressing mode. So for example, if we take move hash 200 comma r naught, so 200 is nothing but the immediate value, that is a constant value. Okay, so sharp sign indicate the front of the value, that value is used as an immediate operand. Okay, so this is how we're going to represent opcode rs comma rt comma immediate, that is the I type. So for immediate instructions, you're going to mainly use the I type instructions, right? So next one is the registers. So registers, what are you going to do? So mainly here the operand you're going to use it is a register. That is a move r1 comma r2 means you're going to use all the six fields. That is a R type. Okay, R type instructions. We said that instruction type falls under the three types. Yeah, R type, I type, and J type. So this falls under the R type, right? Same like that for base or displacement, right? Then PC relative, pseudo direct. Pseudo direct is something but it is a jump instruction where you're going to jump to the particular location. So this is about the addressing modes we are going to have, right? So with this we conclude the sessions of a MIPS instruction format. So thank you all.